Hi everyone. In this part of the talk, I'm going to relate the construction of XPQ and that of YPQ that we just saw, and also analyze the graph of YPQ, which will then later on will enable us to show that XPQ and YPQ are actually isomorphic under some condition, and in particular that XPQ is connected because YPQ is kind of clearly connected. Okay, so let's start by reminding ourselves how is XPQ was defined in kind of a diagram, and then we are going to add some arrows and vertices to this diagram, forming a commutative diagram in which both XPQ and YPQ appear, and then it will be kind of easier to kind of literally see the relation between XPQ and YPQ. Okay, so if you remember, XPQ was defined to be as the Cayley graph, assuming P is 1 modulo Q, whose group, like the vertex that corresponds to PSL2. Otherwise, for P equals 3 modulo 4, you need to take the coset of that, but let's stick with P equals 1 modulo 4. And the generating set was SPQ. And how does it work, right? We started with SP. Don't worry about this thing for a second, but we started with SP. This P plus 1 kind of selected quaternions of norm P, integral quaternions. And then we took their mode Q, their coefficient. That was this map tau Q. Right? Nothing super interesting here. And we showed, well, at least, we showed that all of those, in fact, everything in delta prime, not only goes to an FQ quaternion, but an invertible FQ quaternion, just because the norm, which is the determinant under this isomorphism, is non-zero. It's P, so it's non-zero. And then the second step was moving from this FQ quaternion, invertible quaternion, to a 2x2 matrix, invertible matrix. This is the GL2Q. This is the isomorphism I was talking about, right? So you take this quaternion, you move to a matrix that looks something like that, using those X and Ys. And finally, so there were three reductions. We treated the matrix that we got projectively. Namely, we mod out scalars, or if you want, we consider these modulus transformations. And then we said that SP under this transformation goes to PSL2Q, not just PGL2Q. Okay, so that's why the Cayley graph is on this vertex set. You don't reach using the generator that starts from SP for these reductions. You don't reach anything that's not in PSL2, other in PGL2. And we currently don't know that we reach everything. We don't know that this graph is connected. We don't know that every element here is generated by this generating set, where SPQ is just the image of SP under these reductions. Okay, so that was XP. Imagine you remember that, maybe not in this diagram form, but you remember that more or less. And let's now add YPQ here to the picture. So this is the same diagram from before, but now I added all of these. Okay, so, and this is XPQ from before, and I want to talk about YPQ. So what's happening in this new part? So the construction of YPQ also started with SP, but now considered also as a subset of lambda prime, like the bigger lambda prime quaternions. And we first did this kind of slightly weird reduction, where we identified two integral quaternions if one of them is obtained by the other by scaling of P to some power plus minus. That came from the uniqueness of factorization that we had for quaternions. And yeah, we got this Q, that's just a projection. We got lambda. Right, so these are classes. Alpha goes to alpha, the class of alpha under this equivalence relation. We said tau Q generally is a map from integral quaternions to FQ quaternion, just modeling out by Q. And we said that when you restrict that map to lambda prime, then that map descends in a well-defined manner from lambda to this quotient group, right? So I mean, if alpha and beta are equivalent under the relation, then pi q will map their difference, namely the inverse of the one times the other, to zq. And so tau q descends to this map, which we called pi q. It's just tau q, but you know, descended down. And you know, okay, and this is just the projection map, the natural projection of modulo zq, and so this diagram commutes. And using q, this q and capital Q and pi sub little q, we defined the graph ypq, right? So ypq is the Cayley graph whose vertex set is the image of this map, which we identified as lambda over lambda q by the forced homomorphism theorem. Lambda q is just a kernel. It was defined to be the kernel of this map. And tau pq is just the image of sp under q and pi q. Okay, so like pictorially, ypq sits here and xpq sits here. Now, if you think about it for a second, psi q also descends in a well-defined manner from this quotient group to this quotient group, the projective, because in both cases you just mode out by scalars. Right, I told you that CQ is actually isomorphic to FQ star, and also GLQ, the projective group is modding out by scalar matrices this group. So also psi q descends in a well-defined manner from here to here, and that's the definition of beta. And so beta is just psi q applied here, and so this diagram also commutes. Okay, so everything commutes. So y sits here, x sits here. Everything is quite abstract, I agree. And this is the beta is sort of defined in a roundabout way, connecting the two. Okay. So hopefully this is somewhat helpful. Now we know that ypq is connected, right? Because I mean, we know that I forgot how we call this graph, but we know that that graph that I forgot its name is p+1, yeah, regular tree, right? So before projecting the Cayley graph on lambda and QSP is a p-regular, p+1 regular tree, it's connected, and ypq ypq is obtained, I mean, this graph. So this is the vertex set, right? I'm not mistaken. Yeah, Q of SP, right, exactly. So the graph here, if you take the Cayley graph on lambda and QSP, that's the p+1 regular tree. And when you quotient it modulo Q, connectivity remains because you can kind of pull back from the connectedness of this graph. Right, if you want to, okay, it's a little exercise. So we know that Y is connected. And we want to use that in order to show that X is connected. So we know that Y is connected, but you know, we don't quite understand why. I mean, what is Y? Like the vertex set of Y is the image of pi q, which is whatever. You just need to understand. It's not that difficult, but we need to figure out what does it mean to be an invertible integral quaternion modding out by essentially FQ star. It will be slightly more convenient to look at it as, again, using the forced homomorphism theorem, just trying to understand what lambda of Q is, and then we know what the quotient is. But generally speaking, we don't yet understand the vertex set of Y, and we do understand the vertex set of X. It's just a PSLQ. So we know something about X and we know something about U, and there are some things we don't know. We know Y is connected, but X is not connected. And we want to play these two constructions against each other so that we can, fill the gaps. Right, so that's what's written here. And just know that beta of TPQ is SPQ. So if I'm going back to this, at this point, horrible diagram, TPQ sits here. Right, TPQ is just the image of SP under these two maps. And SPQ is here. It's the image of SPQ under these maps, but it's also, because of the commutativity of the diagram, it's the image of SPQ under, going through the bottom part of the diagram, which really just means that SPQ is a beta of tau PQ. It's a mess. So this means, if you think about it for a second, that we know at least one thing. We know that YPQ is a connected component of XPQ, right? Because we don't understand the vertex set, but we know that beta take the vertex set of Y, which is this thing, to here. So it's a subset of the elements of the vertex set of X. And the generators, TPQs, which generate all of these elements, through beta also generate the image under beta of these vertices. So X contains Y as a subgraph which is connected. And what we are going to show, again, it will take a little bit of time, more time than I imagined, is that, well, assuming Q is large enough, you will see why, then XPQ is actually isomorphic to YPQ, which will make XPQ a connected graph, because Y is. And so the first thing, the first order of business is to understand the vertex sets of Y, which is in lambda over lambda Q, so we need to understand lambda Q. And that's easy, actually. Lambda Q, I mean, if you remember what lambda is even. So lambda, I actually forgot what lambda is for a second. So lambda prime is all of these quaternions that have that, their norm is a power of P. You only stick with power of P elements, integral quaternions with norm which is a power of P. And you have these, maybe slightly weird parity property of your elements. This just, comes from the fact that we chose P+1 out of the 8 P+1 elements in a manner that identifies them, according to who is the odd element. And so that's reflected in this definition. So this is lambda prime. Lambda is quotient out modulo this equivalent relation. And lambda q is the image of pi q. It's somewhere here. Yeah. Lambda q is the image, is the kernel, sorry, of pi q, where pi q take class of some integral quotient from lambda prime to its modding out by q, but modding out by zq, up to essentially a scalar. So that's lambda q, and let's understand it better. So what I'm saying is that lambda q consists of all these classes in which the first coefficient can be anything. Actually, it cannot. We'll see, but you can write it like that. Whatever it is, all I require is that the other three coefficients are divisible by q. Okay, so lambda q contains exactly all of these quaternions whose kind of imaginary parts are divisible by q. They are zero modulo q. And the proof is easy, just following the definition. So take a class of alpha in lambda q. Lambda q is the kernel of this map. And so the fact that the class of alpha goes to lambda q means that tau q of alpha sits in zq, right? Because pi q, you can see it here. So pi q goes to these invertible quaternions modulo zq. So if this thing goes to 1, then the 1 here is just this the thing we mod out by. So tau q of alpha is in ZQ. Now, being in ZQ, if you remember the definition of ZQ, these are all the invertible quaternions modulo Q that are real, namely, right? So they have no imaginary parts, which just means that the imaginary coefficients are divisible by Q, and the real one is indivisible by Q, right? It should be invertible. And once the imaginary parts are divisible by Q, the only thing left are for the real part to be non-divisible by Q. So that's what's written here. So the real part is divisible by Q, is not divisible by Q, and the others are. But I claim that this is equivalent, that's what I hinted to above, to just saying that, I mean, this is implied by this. And the reason is that, look at the norm of alpha. On one hand, it's some power of P. On the other hand, it's just the sum of squares of the coefficients. And so what are the coefficients? So you have a squared 0 plus, something that is divisible by q, even q squared, really, because all of the ai's of the imaginary parts are divisible by q. But anyhow, it's q plus something. So you get that, a squared, a0 squared plus q times something equals p to the m. So if you mod out by, if you take modulo q, you see that a squared, I mean, you see that a squared, a0 cannot be divisible by q because p is, another prime. It's co-prime to q, right? Okay. So we know what lambda q is. That's what I'm saying here. And yeah, and maybe in the next video, because it takes a little bit more time, we are going to show that the graph of ypq is at least 2 of log to the base p of q, which is kind of quite huge. Actually, it's quite close to optimal. As I'll later say, the graph is at most essentially that. Okay, we'll talk about it later. So anyhow, the plan is to show that the graph is large. I don't care about the graph for the purpose of this seminar, but it's part of the proof for the connectivity anyhow. And then afterwards, we'll show the main theorem, which says that, at least of this part, which shows that, assume P is at least 5 and maybe congruent to 1 modulo 4, because we're working with PSL2 and not the coset. And assuming Q is sufficiently large, and P is a square modulo Q, all of these assumptions that we gathered, then XPQ is connected, and therefore it's isomorphic to YPQ. So that will take us back to this meta-abelian property that we have of PSL2Q and so forth. So next order of business is to show that the graph is large and then do the theorem. And by that, we are going to finish with what was supposed to be a 2-hour lecture, which I think is a 2-hour lecture. Okay.